Good morning, all of you. I'm Libu Manjakkal, working as a research associate in University of Glasgow, one of the Department of Electronics and Nanoscale Engineering. I'm working with Professor Ravinder Dahiya. Today, I'm going to discuss with one of my recent research work related to flexible supercapacitor with sweat equivalent electrolyte for safe and eco-friendly energy storage devices. Recently, we noted about the importance of wearable bioelectronics technology or wearable sensors for many applications, which include healthcare or fitness management. So, when we considering wearable systems, the major requirement for wearable systems are sensors, of course, sensors, and to transfer data or sensor can monitor any physical, chemical, or biological parameters, which include our sodium ions, potassium ions, or pressure sensors. So, and to transfer this data, we need associated components like the communication system. For powering all these sensors and communication system, one of the major requirement is energy storage devices or energy generators. There are many energy generators, including solar cell, flexible solar cell, the wearable one, or a triboelectric nano generators, piezoelectric nano generators, and the recent research work are progressing in the fields of biofuel cell also. Uh, all these sensors or energy, the key challenge is the sustainable materials, because when wearable system, when it comes into a wearable, it take to be biocompatible. So in a biocompatible terms of the major electrodes, sensitive electrodes, both sensitive electrodes and electrolyte and the fabrication substrate also. And also when we're talking about energy storage, normal you know that in a battery there is a lot of electrolyte which is acidic or alkaline. So normal lithium ion battery may have a lot of disadvantage in wearable systems because of heating or if it is any broken electrolyte leaking. So the technology is looking forward to operate those sensors and associated component sustainable energy storage systems. So here I'm focusing more about this type of energy storage. For example, wearable supercapacitor. Why supercapacitor is that supercapacitor have a huge potential for powering sensors or associated components in a short period of time. As you can see that which shows a very high energy density in terms of milliwatt per centimeter square, and also power density in watt per centimeter square. In the advanced sensing technology or associated component, you can see that the power requirement is in terms of microwatt or a nanowatt. For example, recently we found some pressure sensor which required 20 nanowatt centimeter per square as a energy devices, as a requirement of power. So in these cases, supercapacitor is one of the most suitable one. The major advantage of supercapacitor is its fast charging time and long life cycles and high flexibility and no thermal breakdown. And also you can see here in the picture when we integrate this with a hybrid technology. For example, one of the lack of supercapacitor is that holding charge for a long time. So this can be overcome by using a solar cell, a flexible energy storage energy generator, and then powering through a sensors. Here you can see one of the integration technology which we did for our recent work in a wearable supercapacitor, and is recently published in Advanced Material Journal. So in wearable supercapacitor, until now the majority of the supercapacitor fabricated either in a textile based substrate or in a flexible substrate, and like a polymer PVC or a PET substrate. In this substrate, normally gel electrolyte or a ionic electrolyte or a acidic or alkaline electrolytes are using for a fabrication of the supercapacitor. When we're talking about sustainability or the problem of biocompatibility, these electrolytes have issues. To overcome that issue, what I used sweat as an electrolyte. Why sweat? In sweat contain huge amount of ions such as positive sodium ions, potassium ions, and calcium ions, and many other analytes including lactose or glucose. So sodium and potassium is almost sodium or chloride ion is the major constituent of a human sweat. and that depends on the human health condition and various other factors, also physiological factors. So when we use these positive ions or negative ions in a supercapacitor, that can be act as a electrolyte in our device. So I fabricated a textile based supercapacitor based on PEDOT PSS as an active electrode, and when during the exercise or when the setting, during setting, these ions are absorbed on the surface of the electrode and it involved in the electrochemical reaction. And here you can see that how we fabricated the devices. Here we have a cellulose polyester cloth, and then we coated with the PEDOT PSS. This PEDOT PSS is modified with the DMSO, dimethyl sulfoxide, to change the conductivity, to enhance the conductivity. Initially we compared the performance with the pure PEDOT PSS and the DMSO, and I'm going to discuss about in later slides what is the performance of this. And then in PEDOT PSS is an excellent polymer, conductive polymer, and here you can see here the pure cellulose cloth and then coated with a PEDOT PSS, and the same image, the one of the fiber of the cloth where the material is strongly adsorbed. And what happened is that when we applied, when the electrolyte comes into contact with this electrode, these two electrode, we have a stacking of such a two electrodes. As you can see here in the slide, the fabrication steps, the single electrode fabrication and stacking of such a electrode with a cellulose, either cellulose, again cellulose polyester as a separator. I used a separator as a cellulose polyester, and then when we applied a potential, the positive or negative ions from the electrolyte separated into the depending on the polarity of the electrode. And here, due to the conductivity of polymer, there are two reactions happen. One is electrochemical double layer formation, and another is a redox reaction in the conjugated polymers, because PEDOT PSS have some complex reaction occur in the electrochemical reaction. And we carried out the major studies, such as initially we did the PEDOT PSS alone, the PEDOT PSS, how the electrochemical, the supercapacitor performance with set equivalent electrolyte. For this purpose, we prepared a set equivalent electrolyte in our lab, and also we tried with a human sweat in the final product, and compare the performance, such as you can see here how the reaction occur for a pure PEDOT PSS and a PEDOT PSS with the DMSO. You can clearly see that when the conductivity enhance due to DMSO, the performance of the charge storing ability of the supercapacitor is increased, and that you can see here the impedance value, the resistance value decreased almost 5 order less with increasing the DMSO content in the electrode. And also you can see here how the capacitance variation with the PEDOT PSS, the device shows almost 10 millifarad per centimeter square capacitance. And for this work, we carried out different studies, include, because electrolyte, human sweat, maybe the sweat producing depends on the exercise or a physiological status. So what I did that I carried out different volume of set, for example 20, 50 and 100 microliter volume of set influencing on the supercapacitor. And also during the exercise or bending, there may be chance of bending, different bending cycles were carried out, and charging discharging ability up to 6,000 cycles for long cycles also were measured. And of course, the last study I did washability test. Here there are a lot of I found washability have some issues. This may be need to overcome in the future work. Here, the one of the image, you can see that how the supercapacitor attached on the curve. This is a small device for testing in bendable studies. Here you can see the difference of performance of the textile supercapacitor in a set equivalent electrolyte and a human set as an electrolyte. In a set equivalent electrolyte, you can see the impedance Nichols plot. You can see how the resistance value, impedance value is varying, and also the cyclic voltammetric analysis with different operating voltage. In a wearable senses, majority of the components or electronics components required 1 to 1.5 electron voltage, 1 to 1.5 voltage for operating volt. So I carried out the studies in up to 1.4 volt. The reason is that in a sweat, the water is the major component. So water dissociation occur at 1.32 volt, and we found that this supercapacitor can work up to 1.31 volt. And here you can see that galvanostatic charging discharging at different current density, and put a high current density 0.83 ampere per gram, the device is showing a still good performance. And in a set equivalent electrolyte, you can see the in a human set as an electrolyte, you can see the performance here. Initially the capacitance without any sweat in the picofarad stage, and when increasing the sweat, you can see here in the almost stable capacitance observed at almost 5 microfarad with increasing the sweat. And here the cyclic voltammetric analysis, you can observe that, and also the galvanostatic charging discharging analysis. When I compared the performance, I noted that in both devices the performance is almost same, and it is 8.94 farad per gram. And here I did an analysis with a different volume of the set, how the influence of different volume of the set in the electrochemical performance. You can clearly note that in 20 microliter, the device shows a charge transfer resistance, and you can see it from the impedance plot here in the value, and it is in almost 600 to 700 ohm. But when increasing the volume, the amount of volume means the wettability. When the wettability is increasing the electrode, the contact resistance of the electrode is decreasing. That you can see that at 100 microliter the device shows an excellent performance. And also similarly, you can see the phase angle. Phase angle is directly related to the capacitance, that you can see here in for an ideal capacitor, the value should be almost 90 degree, and that you can see here in a sweat volume 20 microliter. This is the capacitance is in 50, and then the phase angle is in 50, and when increasing the volume of the sweat, you can see here it almost reached 80 degree. And also with increasing the volume, you can see the cyclic voltammetric pattern, and at 100 microliter it shows an excellent performance. Next, I carried out how the supercapacitor influencing on different charging discharging cycles. For example, I did the initial cycle. You can see here the charging discharging analysis, and it shows an IR voltage drop on 0.0180 18 millivolt. But with increasing the 4000 cycle, that you can see a single electrode in a positive potential, and then how the charging the impedance spectroscopic analysis in almost 10 ohm resistance value. But when increasing the number of cycles after 4000 cycles, you can see that the potential drop is almost increased. And the reason behind this is that the material or the electrolyte got evaporated, because after 4000 cycle the sweat evaporated, and then that significantly affect the electrochemical performance. That you can see here, the from 10 ohm it is increased into 200 ohm. Then again what I did, that I drop again the sweat, because the device is still working, and I again drop the sweat and test the performance. But and I noted that after 4000 cycle it doesn't go back to the state of the first cycle, initial cycle, but it shows a significant performance after 4000 cycle itself. You can see here the value is come down in the 50 ohm range. And so this means that such evaporation occur during long cycle. There is a evaporation of sweat, but the major advantage is that we can easily refill the sweat into the textile. Then the device will work again. But some of the drawback in the working performance is due to the material degradation. And you can see here the comparing performance of different volume, and also bending radius. I did almost similar performance observed. And this is the conclusion. And almost 100 millivolt per second, I got a 7.18 millifarad per gram, and the energy density in almost 1.36 watt hour per gram, and it is almost same performance with the electrolyte. And thank you, my team members and the funding agency Aquasens. And if you have any doubt, you can contact my supervisor, and also you can send me an email. Thank you so much.